Welcome to an introduction to vector fields. The goals of this video are to define a vector field and then also to graph a vector field by hand and with technology. A vector is a quantity with magnitude and direction. Here we see two black vectors that represent the speed and the direction of the yellow and blue car. So the arrow points in the direction of motion, and then because the yellow car has a longer vector, its magnitude would be larger, which means the yellow car is going faster. For example, this car may be going 75 miles per hour, and the blue car may only be going 35 miles per hour. Again, the arrow points in the direction of motion, and the length or magnitude of the vector represents how fast the car is going. So functions that assign a vector to a point in a plane or a point in space are called vector fields, and they are useful in representing various types of force fields and velocity fields. So let's take a look at a formal definition of a vector field. A vector field over a region R in a plane or in two dimensions is given as we see here, where f of x, y is given as the vector where the x component is a function of x and y, and the y component of the vector would be given as a function of x, y. And f and g are continuous over the region R. And for three dimensions, the vector field will have three components given by f, g, and h as functions of x, y, and z. Again, f, g, and h are continuous over the three-dimensional region or space V. So one thing to notice is that the gradient that we've already talked about is an example of a vector field. Before we graph our own vector fields, let's take a look at some two-dimensional vector fields created in Mathematica. Here we see the force field given by f of x, y equals the vector field x comma negative y. Again, notice each vector has an arrow giving it direction as well as a length, which will be given by the magnitude, which represents the amount of force at a given point. What we see here in red is if we had a point in this field, based upon the force given by the field, the red path shows the direction that point would take. So if we move this point somewhere else, you can see the force would be in a different path. And here's another two-dimensional vector field. Again, if we move the position of the point, its path will change based upon the force of the field. Let's go and take a look at one more. Here's an interesting one. So again, if we move this point to some other location in the field, its path will change based upon the forces in that location. Here's one more that I wanted to show. Here's the equation of the vector field, and here's the graph of the vector field. And you can see here that it creates several circular motions. Some of them are clockwise, and some of them are counterclockwise. Now let's take a look at a few vector fields in three dimensions. Here's the graph of the vector field f of x, y, z equals x comma y comma z. And again, each vector in the field gives us a direction as well as a magnitude, where the length of the vector represents the amount of force at that point. So you might be able to think of this vector field as an explosion from the center of this box. Here's the three-dimensional vector field given by f of x, y, z equals negative y, comma, negative z, comma, x. You can see here that the motion of this vector field is more of a circular motion, where in the first example the direction was outward. Let's take a look at how we can graph a two-dimensional vector field by hand. To graph a vector field by hand, we need to plot several vectors in the vector field by selecting x and y values in the coordinate plane and then plotting the corresponding vector. And sometimes it is helpful to plot several vectors with the same magnitude. However, graphing software is very helpful in plotting vector fields. Let's take a look at a couple of examples. Here we want to graph f of x, y equals negative 1, comma 1. So notice that this vector field is not affected by the values of x and y. Every single vector in this vector field would have an x component of negative 1 and a y component of positive 1. So we'll start at the origin and move left 1 unit and then up 1 unit to represent our first vector in the vector field. Now what we'll do is go ahead and space these 1 unit apart all along the x-axis. And now we'll go ahead and do the same along the line y equals 2. So again, the x component will be -1 and the y component will be +1. So it looks just like this, all along y equals 2. And let's go ahead and do the same at y equals -2. And notice how I skipped y equals 1 and y equals -1, and I could have sketched vectors there, but notice how they would have run into the vectors along the x-axis. So when creating a vector field, you do have to decide how far you want your vectors spaced apart, because there are several ways to represent an accurate vector field. Here's the same vector field created with Maple. You can see here it's much more thorough and obviously a lot faster. Let's take a look at another example. Here we have f of xy equals 0, -x. So again, we'll pick points on the coordinate plane and then sketch the corresponding vectors. Notice that each vector is only affected by the value of x. So what we'll do on this vector field is select a value of x, let's say x equals 1. So all along this vertical line x equals 1, each vector would have an x component of 0 and a y component of -1. So if we start at +4, we'd plot the vector 0, -1, which would be here. Let's go ahead and jump down to this point here and plot the same vector. Skip down to y equals -1, plot the same vector, -3, plot the same vector. Now if x equals 2, that would be along this vertical line here, and every vector along that vertical line would have an x component of 0 and now a y component of -2. So if we started here at 4, we'd have a vector 0, -2. Now I'll go ahead and jump down to y equals 1, plot the same vector, jump down to y equals -2, plot the same vector. And let's go ahead and try x equals 3. You probably can see the pattern now. Every vector will have an x component of 0 and a y component of -3. So if we start up here at y equals 4, we'd go down to y equals -1. If we start here, we go down to y equals -3. Let's take a look at some negative values of x now. When x equals -1, along this vertical line here, every vector would have an x component of 0, but now the y component would be +1. So it's very similar to, except now they'll be in the opposite direction. So if we start up here at y equals 3, the vector 0, 1 would look like this. At y equals 1, it would look like this, and so on. And again, I'm purposely spacing these vectors apart so they don't run into each other. And when x equals -2, each vector would be 0, 2. So if I start here at y equals 2, along the line x equals -2, 0, 2 would look like this. I'll jump down to here, 0, 2 would look like this, and 0, 2 would look like this. So you can see that when x is positive, the vector field is moving downward, and when x is negative, it's moving upward. And as x moves to the right, the magnitude increases, as well as if it moves to the left, the magnitude increases. Using some software, the same vector field would look like this. And let's go and take a look at one more. Here we have the vector field f of xy equals x, y. And for this one, we are going to plot vectors that have the same magnitude. So the magnitude of this vector would be the square root of x squared plus y squared. And we're going to let this equal some constant c, pick some values of c, which would tell us the magnitude of the vectors, and then we'll also sketch the level curve, which would be where the initial points of those vectors would occur. What I mean by that is if we let c equal 1, that means the magnitude of each vector would be 1, and those vectors would occur along the level curve where x squared plus y squared equals c squared, or 1 squared, or in this case just 1. Well, that's a circle with a radius of 1 centered at the origin, and all along here each vector would have a magnitude of 1. So if I start here at the point 0, 1, if x is 0 and y is 1, this would be our vector. If x is 1 and y is 0, this would be our vector. And at 0, -1, this would be the vector. And at -1, 0, this would be the vector. Again, subbing in the coordinates into the formula for our vector field. Now let's let c equal 2. If c equals 2, that means each vector would have a magnitude of 2, and it would occur along the level curve where x squared plus y squared equals 2 squared, or 4. Well, that's a circle with radius 2 centered at the origin. So now we'll plot vectors along this level curve, and each of them will have a magnitude of 2. So if I pick the point right here, where a 45-degree angle would intersect that circle, I know that the two legs of the reference triangle would be equal, which is what we want because the x and the y components are equal to each other. So I know that I would go out 2 units here along a 45-degree angle. And the same thing for each 45-degree reference angle in each quadrant, the vector would form a 45-degree reference angle. And each vector has a length of 2 units. And we could pick another value for c, but we're going to go ahead and stop here and take a look at the computer-generated vector field. And here it is, and you can see if we were to sketch the level curves, the vectors with the same magnitude have their initial points on a circle centered at the origin. I hope you found this introduction helpful. Thank you for watching.